Welcome to PhDAI730 Lecture 3. This is your Professor T. Freed Muhammad. In this week, we will explore the principles and applications of Bayesian statistics with a particular focus on Bayesian inference and Markov chain Monte Carlo, which is a continuity of our previous discussion, methods, and their pivotal role in the field of artificial intelligence. Bayesian statistics offers a dynamic approach to data analysis by incorporating prior knowledge into the statistical process, which is especially valuable in AI for making informed predictions and decisions under uncertainty. Using Python, a leading programming language in artificial intelligence, as we are all aware of that, we apply Bayes' theorem to update the probability of hypothesis as new data becomes available. This method enhances AI models by permitting them to learn and adapt from observed data, making Bayesian inference a cornerstone in developing intelligent systems capable of handling complex real-world scenarios. Bayesian statistics. Let's look into this in a little bit more depth. The Bayesian statistics plays a transformative role in artificial intelligence by providing a robust framework for reasoning under uncertainty. Unlike traditional statistical methods, Bayesian approaches allow artificial intelligence systems to incorporate prior knowledge and continuously update their beliefs as new data is observed. This dynamic adaptability is particularly valuable in artificial intelligence, where models often operate in complex real-world environments with incomplete or noisy data. By treating probability as a measure of belief, Bayesian methods enable AI systems to make more informed and nuanced decisions, even when faced with ambiguity. This capability is essential for applications ranging from medical diagnosis to autonomous driving, where uncertainty is inherent and the cost of errors can be high. In artificial intelligence, the ability to learn from limited data is a significant advantage of Bayesian statistics. Many AI models, especially deep learning systems, require a vast amount of data to achieve high performance. Bayesian methods, however, can deliver reliable results with smaller datasets by leveraging prior information. This efficiency not only reduces the dependency on big data, but also enhances the interpretability of AI models. For example, in personalized medicine, Bayesian inference can help tailor treatments to individual patients by combining general medical knowledge with patient-specific data, leading to more accurate and actionable insights. Bayesian statistics fosters transparency and trust in AI systems. By quantifying uncertainty, Bayesian models provide not just point estimates, but also confidence intervals, permitting users to understand the reliability of predictions. This transparency is critical in high-stakes domains like finance, healthcare, and autonomous systems, where decisions must be both data-driven and explainable. As AI continues to integrate into society, the principles of Bayesian statistics will remain pivotal in developing intelligent systems that are not only powerful but also accountable and aligned with human values. Role of Bayesian statistics in artificial intelligence. Bayesian statistics is increasingly being applied in business process outsourcing to enhance decision-making and operational efficiency. BPO industries, which handle vast amounts of data such as customer service interactions, transaction processing, and quality assurance, can leverage Bayesian methods to improve accuracy and adaptability. For instance, Bayesian inference can be used to predict customer behavior, optimize resource allocation, and identify fraudulent activities in real time. By incorporating prior knowledge, such as historical call center or transaction patterns, Bayesian models can dynamically update their predictions as new information flows in. This allows BPOs to respond more effectively to changing conditions, reduce operational costs, and deliver high quality services to the clients. A practical example of Bayesian statistics in BPO in customer churn prediction can be taken as a use case. Suppose a BPO firm manages customer support for a telecom company. Using Bayesian inference, the firm can analyze past customer interactions, such as call durations, complaint frequencies, and service usage patterns to calculate the probability of a customer churning. As new data comes in, like a recent spike in complaints or drop in usage, the model updates its predictions, enabling proactive interventions such as targeted retention offers or personalized support. This is not only improving customer satisfaction but also boosting client retention rates, demonstrating how Bayesian methods can drive tangible business values in the data driven industry like BPO is an example. And obviously, the role of Bayesian statistics in AI handles uncertainty and incomplete data, missing values, or erratic information that is coming in the customer support, incorporates prior knowledge. On the basis of previous interaction with the customers, it allows us to look into that, the possible plausibility. Adaptive learning in AI models, as just discussed, in terms of customer churn predictions for you to look into. The probability utilization in Bayes' theorem allows us to work with a priori or prior, likelihood, and posterior. Evidence comes after all applying this Bayes' theorem. You are most welcome to look at one of my research papers, The Evident Use of Evidence Theory. It is on Google Scholar available for you to look into. So let me give you an example, a smaller examples to make you realize that how important this prior or a priori, likelihood, and posterior are. Bayes' theorem is a fundamental concept in probability theory that describes how to update the probabilities of hypotheses when given evidence. At its core, the theorem provides a way to revise existing predictions or beliefs known as the prior probability in light of new information, resulting in an updating probability, the posterior probability. Mathematically, as it is expressed on the screen, the P of A given B is the posterior probability, the likelihood of hypothesis A being true, given the evidence B, whereas B given A is the likelihood of observing the evidence B if A is true. The probability of A is the prior probability of A, and probability of B is the total probability of observing B. Bayes' theorem bridges the gap between what we already believe and what we observe, making it a powerful tool for decision making under certainty. A classical example of Bayes' theorem in action is medical testing. Suppose a disease affects 1% of the population, and the test for this disease is 99% accurate, meaning it correctly identifies the disease in 99% of infected individuals, true positive, and correctly rules it out in 99% of healthy individuals, true negatives. If David tests positive, that is the probability he actually has the disease. Intuitively, one might assume a 99% chance that Bayes' theorem reveals a different story. Let's say 1,000 people are tested. 10 would truly have the disease 1% prevalence, and those 9 would test positive, 99% accuracy. However, 990 healthy individuals would also be tested, and 10 of them, which is 1%, will receive false positives. Thus, out of 19 positive results, 9 true plus 10 false, only 9 are accurate. The posterior probability that David has the disease given a positive test is just 9 over 19, or approximately 47%. This example highlights how Bayes' theorem accounts for both tests' accuracy and a disease's rarity, providing a more nuanced understanding of risk. This principle is widely applicable beyond medicine, from spam email filtering to financial risk assessment. For instance, email providers use Bayesian filters to classify messages as spam or legitimate. The filter starts with a prior probability based on historical data. Words like free or win are common in spam. As new emails arrive, the filter updates its beliefs by calculating the posterior probability that a message is spam given the presence of these words. Over time, the system becomes more accurate, adapting to evolving spam tactics. Bayes' theorem ability to incorporate new evidence makes it indispensable in fields where decisions must balance prior knowledge with real-time data, ensuring more informed and adaptive outcomes. So now let's look into Bayesian inference with another example. The Bayesian inference allows, let's take example of manufacturing facility. So let me reinstate. Bayesian inference allows manufacturers to refine their predictions by combining prior knowledge with new data. In a manufacturing setting, this means using historical production data, quality control records, the real-time sensor readings to continuously update the likelihood of defects, equipment failures, or process inefficiencies. So the formula, as we discussed, was P given probability of A given B, and which was equal to probability of B given A multiplied by probability of A divided by probability of B in totality. Here, probability of A given B represents the updated probability of an event A, such as a machine malfunction, given new evidence B, like an unusual vibration or temperature spike. For example, if a factory manager, let's say him Oscar, wants to assess the risk of a production line failing, Bayes' theorem helps integrate the machine's past performance, prior probability, with real-time diagnostics likelihood to provide a more accurate risk assessment posterior probability. This approach enables proactive maintenance, reduces downtime, and improves overall efficiency in manufacturing operations. Consider a real-world scenario in a car manufacturing plant. Suppose a specific assembly line has a 5% historical failure rate, and a new sensor system detects early warning signs with 95% accuracy. If the sensor alerts Oscar to a potential issue, what's the probability that the line will actually fail? Bayes' theorem helps calculate this. Out of 10,000 production cycles, 500 might historically result in failures, which is 5% prior probability or a priori. And the sensor would correctly identify 475 of those 95% accuracy. However, the sensor might also flag 500 false alarms out of 9,500 successful cycles, 5% false positive rate. With 975 total alerts, 475 true plus 500 false, the posterior probability of an actual failure given an alert of 475 divided by 975 in totality, or approximately 49%. This calculates for Oscar to prioritize maintenance efforts, focusing on the most critical alerts while minimizing unnecessary downtime. Beyond predictive maintenance, Bayesian inference is used in quality control and supply chain optimization. For example, if a batch of raw materials arrives, Bayesian models can update the probability of defects based on supplier history and incoming inspection data. This adaptive approach allows manufacturers to make data-driven decisions, such as adjusting production schedules or reordering materials before issues escalate. By continuously refining predictions with real-time data, Bayesian methods empower manufacturers like Oscar to enhance productivity, reduce waste, and maintain high quality standards in a competitive industry. Prior versus posterior, as we have discussed this in quite depth, the prior is initial belief before seeing the data. Posterior is updated belief after seeing the data. Understanding likelihood, probability of observing data given a hypothesis, as we discussed earlier. Role in updating posterior, how we figured out 475 out of 975, which was 49% calculation that helped Oscar to prioritize maintenance efforts, as we discussed. Conjugate priors. Priors that result in posteriors of the same family. The beta binomial model is, I suggest you strongly to look into and conduct research on beta binomial model to establish your understanding in more depth. Bayesian versus frequentist. Let's look into this in a little bit more depth. Let's dive into a real life example of route optimization. Bayesian and frequentist statistics offer distinct approaches to solving real world problems like route optimization in logistics and transportation. The frequentist approach relies on fixed long-term probabilities based solely on observed data without incorporating prior knowledge. For example, if a delivery company wants to determine the fastest route between 2 points, a frequentist method would analyze historical traffic data to estimate average travel times. It treats these averages as statistic truths, assuming that future conditions will mirror past patterns. While this method is objective and works well with large datasets, it struggles to adapt quickly to unexpected changes such as sudden traffic jams or road closures, because it does not account for real-time updates or external context. In contrast, Bayesian statistics treats probabilities as dynamic beliefs that can be updated as new information becomes available. For a logistics manager like Brian, this means starting with a prior belief about route efficiency, perhaps based on historical data or driver experience, and continuously refining that belief with real-time inputs such as live traffic updates, weather conditions, or even social media reports of accidents. For instance, if a Bayesian model initially predicts a 30-minute delivery time but receives live data indicating a traffic jam, it can immediately adjust the estimated time and suggests an alternative route. This adaptability makes Bayesian methods particularly valuable in route optimization, where conditions can change rapidly and decisions must be made on the fly to minimize delays and fuel costs. The strength of Bayesian approach becomes especially clear in scenarios with limited or uncertain data. Suppose Brian's delivery fleet operates in a city with inconsistent traffic patterns due to construction or special events. A frequentist model might stick to the historically fastest route even if it is currently congested, while a Bayesian model would incorporate real-time GPS data, driver feedback, and even predictions from other sources to reroute dynamically. By combining prior knowledge with live updates, Bayesian route optimization not only improves delivery times but also enhances fuel efficiency and customer satisfaction. This flexibility is why Bayesian methods are increasingly favored in modern logistics, where agility and responsiveness are key to staying competitive. MCMC, we have done extensive discussions on MCMC. It is approximating complex posterior distributions, how it works, sampling from probability distributions, as we discussed earlier. The Metropolis Hastings, a core MCMC method. The steps are proposal, acceptance, rejection, and or convergence. So acceptance or rejection, Next is convergence. Example is random walk in parameter space. I would strongly suggest you to conduct a little research on Metropolis Hastings to understand in more depth for your learning purpose. You can use Google Scholar, IEEE Explorer, or ACM databases. Library is the best place to go and conduct this research. Gibbs sampling, a special case of MCMC sampling from conditional distributions, as we just discussed in quite depth of the route optimization. Use case is high dimensional data. In traffic, there the data can be extremely high dimensional if it is in Chicago or in Atlanta, for example. The Gibbs sampling, I suggest you to look into this in more depth to conduct an experiment to enhance your understanding by looking at Google Scholar or IEEE Explorer. Bayesian methods in artificial intelligence, the spam filtering as we discussed in quite depth, recommendation systems on Amazon or Facebook or eBay, autonomous vehicles, Tesla and Waymo and Baidu and all that jazz. The Bayesian neural networks. Neural networks with Bayesian inference, the advantages are uncertainty estimation and robustness. Let's look into this with an example. BNNs are revolutionizing the way sports analytics are conducted by introducing a probabilistic approach to predictions rather than relying on fixed deterministic outcomes. In traditional neural networks, predictions such as game outcomes, player performance, or injury risks are often treated as single point estimates. Ignoring the inherent uncertainty in sports, BNNs, however, model uncertainty by treating weights and predictions as probability distributions. For someone like Boris, as we are taking Boris as our main actor in this discussion, who may be involved in sports analytics or team management. This means gaining not just a prediction or whether a player will perform well in the next match, but also a confidence interval that quantifies the likelihood of different outcomes. This probabilistic insight is invaluable for making informed decisions, such as game strategies, player rotations, or even contract negotiations, where understanding risk and variability is just as important as the prediction itself. A compelling use case for Bayesian neural networks in sports is player injury prediction and prevention. Injuries are a major concern in professional sports, often derailing season and careers. A BNN can analyze a player's historical data such as training load, biomechanics, and past injuries while also incorporating real-time inputs like fatigue levels, game intensity, and even weather conditions. For example, if Boris is working with a soccer team, a BNN could predict not only the likelihood of a key player getting injured in the next match, but also the uncertainty around that prediction. This allows medical and coaching staff to take proactive measures, such as adjusting training regimens or resting players, based on a nuanced understanding of risk. By accounting for uncertainty, BNNs provide a more robust framework for injury management compared to traditional models, which might only offer a binary high risk or low risk assessment. Beyond injury predictions, Bayesian neural networks can enhance game strategy optimization and fan engagement. For instance, coaches and analysts can use BNNs to simulate various game scenarios, accounting for the probabilities of different player actions, opponent strategies, and even referee tendencies. This probabilistic approach enables teams to develop adaptive game plans that consider a range of possible outcomes rather than relying on a single predicted strategy. Additionally, BNNs can personalize fan experience by predicting viewer preferences with uncertainty estimates such as likelihood of a fan engaging with specific content or attending a game, following teams and broadcasters to tailor their outreach efforts more effectively. For Boris, leveraging BNNs in sport analytics means not just staying ahead of the competition, but also creating a data driven culture that embraces uncertainty as a strategic advantage. Bayesian optimization in artificial intelligence, optimizing expensive black box functions, as we discussed with all the data sets in the healthcare and the sports and the route optimization and manufacturing examples. The use case here is hyperparameter tuning. I would suggest you to conduct a little research on hyperparameter tuning. Uncertainty quantification. The importance in AI is safety, reliability, interpretability. Bayesian approach allows us to look at credible intervals, probabilistic outputs, and we have discussed all these in quite depth earlier. The case study problem is diagnosing disease with uncertain data, as we discussed about looking at the COVID testing and all those disease testing in the previous discussion. The solution is Bayesian inference for probability updates, allows us to look into this in depth. Happy learning. See you in the next lecture.